So when we last left off, we discussed many methods to prepare esters, amides, acyl chlorides, and other carboxylic acid derivatives. What we're now going to do is we're going to talk a little bit about naming esters and the process and the rules for ester nomenclature. So esters can really be thought of as a molecule or a functional group with two parts. We have our alcohol side chain and we have our carboxylate side chain. And the reason why I think about esters in this way is because when you name an ester, you name the alcohol side chain, then you name the carboxylate side chain. So first, to name an ester, you number the carbonyl carbon as carbon 1. Then you note the alkyl chain attached to the carbonyl carbon. Next, you number the carbon attached to the ester alcohol oxygen as carbon 1, and you note the alkyl chain attached to the alcohol oxygen. Okay. You then name the alcohol alkyl chain first, then you name the carboxylate group alkyl chain, replacing the suffix with the -ate suffix. So for example, looking at this ester, what do we call this 3-carbon chain? What do we call a 3-carbon chain? Methyl, ethyl, propyl. Yeah, so this will be called propyl. And then looking at our carboxylate side chain, we have an ethyl side chain, but we change the suffix from ethyl to ethanoate. Since ethane is our base name, ethane changes to ethanoate. So this ester would be called propyl ethanoate. Let's do another example. So in this case, we have an ester with a complex alcohol side chain. Remember, we always name our alcohol side chain first. So at carbon 1, we have a chlorine. So we name this 1-chloromethyl because this is a side chain. So rather than chloromethane, this is called 1-chloromethyl. That's our alcohol side chain. And then rather than propane, it's propanoate. Does this idea make sense to everyone? You name your alcohol side chain, then you name the carboxylate side chain, keeping in mind that both the carbonyl carbon and the alcohol carbon attached to the oxygen are designated as carbon number 1. Let's look at another case. What happens if we have substitution on the carboxylate side chain? Well, let's number our carbons here. So first and foremost, we name our alcohol side chain. What do we call a 1-carbon chain? What do we call a 1-carbon side chain? 1-carbon side chain. What do we call that? A methyl group, right? So this would be methyl. Now we name the carboxylate side chain. And in this case, rather than bromo, there's no bromine atom here, this would be 2-chloro. Now, since we have a 3-carbon carboxylate chain, this would be called methyl 2-chloro. Rather than propane, it would be propanoate. Does this example make sense to everyone? Okay, so let's keep going. Let's try to apply what we've learned to name the following ester compounds. So let's start and let's try to name compounds A and B. And I'd like us to take about 3 to 4 minutes as we work through these examples, And then I'd like students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. And remember, you want to name the alcohol side chain first, then you name the carboxylate side chain. So we have a lot of students sharing their proposed responses. So first they name this alcohol side chain as a butyl side chain. We then have a 4-carbon carboxylate chain. So this is called butyl for this 4-carbon alcohol side chain. And then rather than butane, we'd call this carboxylate side chain butanoate, replacing our suffix with the -ate suffix to denote that we have an ester. So this compound would be called butyl butanoate. It's amazing how fast everyone came up with a IUPAC name for this first compound. I saw 5 or 6 responses really quickly in the chat. It's good to see. Any questions on this first example before we begin the second example? Okay, let's keep working on this second example and let's add a structure C. We have a lot of students already beginning to try and name compound B. So let's put some locant numbers into place. So first we name our alcohol side chain. So we call this 1-methylpropyl. And then again, we have a 4-carbon chain. So rather than butane, our carboxylate chain is named as butanoate. So this compound can be called 1-methylpropyl butanoate. Is there another name for this compound? And I'm not talking necessarily an informal name. Is there another IUPAC valid name for this compound? Is there another way to name this 1-methylpropyl side chain? Is there another name for methylpropyl side chain? What do we think? Let's take a moment, as this is actually pretty interesting. What do we call this group right here? It's one of our named alkyl chains. So we have our oxygen attached at the second carbon of this butyl chain. We could also call this sec-butyl butanoate. That's another name for this compound. Far less common. This particular connectivity for our alkyl chain, this is known as a sec-butyl group. Does that look familiar to everyone? Any other questions on this example? Okay, so let's try to name compound C. So in this case, we have a pretty complex ester with functionality and substituents on the alcohol and our carboxylate chain. So adding in our numbers, remember the carbonyl carbon is assigned carbon 1 and the carbon attached to the alcohol is assigned carbon 1. So we have many proposed names. One name that sticks out is 2-chloroethyl, 2-methyl, and this is a 4-carbon chain, so this is butanoate. So we name this compound 2-chloroethyl because the chlorine is at carbon 2. 2-methyl because we have a methyl group at carbon 2, and then butanoate because we have a 4-carbon carboxylate chain. Does this example make sense to everyone? Perfect. Let's keep going now and let's talk about methods to prepare esters. Overwhelmingly, esters are prepared from carboxylic acids. So there are many ways, first of which, and probably one of the more common methods, is the alkylation of carboxylate salts. This is limited to primary alkyl halides. So for example, if you have a carboxylate anion, we can readily displace an alkyl halide via an SN2 reaction only if this alkyl halide is primary and some secondary alkyl halides, so it's not very common. Alternatively, you can install and prepare this ester from the carboxylic acid via a Fischer esterification. However, for your alcohol, you're limited generally to primary alcohols due to the strongly acidic conditions involved. Notice how when we run the esterification reaction in the laboratory, all of our Fischer esterification reactions that we've ran utilized a primary alcohol. If you use a secondary alcohol or a tertiary alcohol, you're likely going to see elimination. Does that comment make sense to everyone? Now, if you really want to install a primary, secondary, or tertiary alcohol as part of your ester, you're going to need to go through the corresponding acyl chloride. The reaction of an acyl chloride with an alcohol via what's known as the alcoholysis reaction is quite general and tolerates a range of alcohols. And this allows you to prepare a range of esters, even with sterically congested or hindered alcohols. Does everyone understand the benefits and limitations of each of these 3 synthetic methods that we've covered? Does this make sense to everyone? Okay, so let's keep going now. And let's talk about the reverse reaction to esterification, which is the hydrolysis, which is a method to convert esters into carboxylic acids. Esters can be hydrolyzed by aqueous base or aqueous acid to yield a carboxylic acid plus an alcohol. So what we're going to do now is we're going to look at each of these hydrolysis mechanisms under acidic and basic conditions. So we'll start with the basic condition mechanism. So if you start with your ester and you treat it with sodium hydroxide, as we're under basic conditions, the first thing that's going to happen is our nucleophilic equivalent of hydroxide will attack the electrophilic carbonyl carbon, generating a tetrahedral intermediate. From here, we're going to kick out our leaving group, which is our alkoxide equivalent. That in turn gives us a carboxylic acid. However, under basic conditions, we have one last trick where our carboxylic acid is immediately deprotonated by our alkoxide ion to generate a carboxylate salt. This sits around in solution until it's quenched with water or another strong acid like H3O+. So this is just during the quench. Does this mechanism make sense to everyone? Any questions on this mechanism? Okay, so let's keep going and let's now look at the acidic mechanism for hydrolysis. So as we're under acidic conditions, the first thing that's going to happen before anything else is that we're going to protonate our carbonyl oxygen. This activates our carbonyl as an electrophile and allows even weak nucleophiles, such as water, to attack and hydrolyze our ester. So now our weak nucleophile, such as water, will attack the carbonyl carbon, and with this will generate a tetrahedral intermediate. Now, this is where things get a little bit interesting. So in order to continue on with this mechanism, as we eventually want to kick out our alcohol leaving group, the first thing that's going to happen is we're going to pull off a proton from our water that just added in to free up a lone pair on oxygen. And then we are going to protonate our, in this case, it's an ether oxygen, to activate this alcohol as a leaving group. After we've completed this proton transfer process, we've now primed our leaving group to leave during this 1,2 elimination step. So we're going to kick down a lone pair, and we're going to regenerate our carbonyl, and we'll lose our activated alcohol leaving group. That in turn generates our highly acidic protonated carboxylic acid that is quickly and almost immediately deprotonated by solvent to give us the desired neutral carboxylic acid. Does this mechanism for the hydrolysis of esters under acidic conditions make sense to everyone? Any questions before we move on? Okay, so let's keep going now. So just as a review for the acid catalyzed condition, we protonate our ester, water attacks, then we deprotonate our alcohol to free up a lone pair. We protonate our leaving group to activate our leaving group. We then kick down a lone pair and we lose our activated leaving group. From here, water pulls off a proton from our protonated carboxylic acid, and that gives us our desired carboxylic acid product. Okay. Just as a review for the base catalyzed ester hydrolysis conditions, it's a typical carbonyl substitution reaction. Hydroxide attacks our electrophilic carbonyl carbon. We collapse and regenerate our carbonyl, and we lose our alkoxide leaving group. From here, we deprotonate our generated carboxylic acid, and this gives us a carboxylate salt. One thing that's important to note is this carboxylate salt is very resistant to nucleophilic attack. So in effect, it helps drive this hydrolysis reaction towards the carboxylic acid product. Because no matter how hard we try, this carboxylate salt is substantially more resistant to nucleophilic attack and carbonyl substitution reactions compared to the parent ester. It's very hard to lose an equivalent of O2 minus. And that's why in the mechanism we show this deprotonation step, and we clearly show that we have a carboxylate salt floating around in solution. Does that discussion make sense to everyone? Okay, so let's try to apply what we've learned, and let's look at the following two reactions, and let's try to predict the product from each reaction and draw a mechanism for each reaction. So in this case, we're looking at, in the first reaction, a base catalyzed hydrolysis of an ester, and the second case, we're looking at an acid catalyzed hydrolysis of an ester. Let's take a few minutes and let's start with reaction A. Let's take a few minutes and let's try to draw a mechanism for reaction A and predict the products from this reaction A. And I'd like students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. And if there are any questions I can address, don't be shy to send them my way. We have a student already beginning to draw out their predicted product, and then there's space in the class whiteboard below to draw the mechanism for this reaction. So we have a student predicting that we'd generate acetic acid as one of our products. And ethanol. Yeah, those two predicted products look reasonable. Would anyone like to try and justify these predicted products by proposing a mechanism for this reaction? So we have a student proposing that sodium hydroxide attacks our carbonyl carbon. We generate a tetrahedral intermediate. Sure. And then that tetrahedral intermediate collapses. Yeah, it looks like the student's drawing the tetrahedral intermediate collapsing. And when it collapses, do we lose our leaving group? So we have a lone pair kicking down. We regenerate our carbonyl. That all looks good. And then can we draw the loss of our leaving group along with that step? Yep, exactly right. We kick down our lone pair, we regenerate our carbonyl, and that gives us our desired hydrolysis product. Perfect. So this student proposed mechanism looks great. So what I'm going to do is I'm going to clear those annotations and just redraw the mechanism, just so that way everything's saved when we export this file onto the class note set. So as the class noted, the first step in this mechanism, if we're looking at basic hydrolysis, is our nucleophile will attack our electrophilic carbonyl carbon, and that gives us a tetrahedral intermediate. From here, the tetrahedral intermediate will collapse and we'll lose our leaving group. Finally, as a last step in this mechanism, our equivalent of alkoxide will pull off a proton, and that will give us our corresponding carboxylate salt product, along with our alcohol. It's nice to see that students noted this deprotonation step in their mechanism, as this really important step helps drive the reaction towards the products and ensure that this equilibrium favors the hydrolysis product. Any questions on this first reaction and this first mechanism? If we don't have any other questions, let's move on to the next example. And let's try to predict the product from the following reaction between ester, hydrochloric acid, and water. And then let's try to justify our predicted product by drawing a mechanism for this reaction. So we have hydrochloric acid. So what do we think? Are we under acidic or basic conditions? Clearly under acidic conditions. Wonderful. Okay, so given that we're under acidic hydrolysis conditions and we have an ester, let's try to predict the product from this reaction. And I'd greatly appreciate if a student would mind volunteering to draw a mechanism for this reaction or to draw the predicted products. Either works. So we have a student drawing out the mechanism for this reaction. First, they show protonation of the ester carbonyl. This activates our carbonyl carbon as an electrophile. From here, the student's now drawing water, which is not the best nucleophile, but it will be more than sufficiently nucleophilic to attack the electrophilic carbonyl carbon to give a tetrahedral intermediate. From here, we now have to activate our alcohol as a leaving group via a series of proton transfers. So the student's drawing first the deprotonation step where we free up a lone pair on one of our oxygen atoms. And we also have to show activation of our leaving group. So in order for us to kick out our equivalent of, in this case, methanol, we're going to need to activate our leaving group. And one of the best ways to do that is via protonation. Did we lose? So we pulled off a proton from our alcohol, and now we have our ester. In this case, we're dealing with a methyl ester. So we have this alkoxy equivalent. So this should be a CH3 group. Now, in order to activate this ester as a leaving group, what do we protonate? If we wanted to activate this ester as a leaving group, what does the class think? What are we protonating here? So looking at the arrow, I would revise this first arrow to show what lone pair is pulling the proton. What lone pair is being used to pull off that proton. So if we wanted to protonate our methyl ester oxygen, we draw an arrow from the lone pair to our proton source. Exactly right, exactly right. After protonation now, we've activated our leaving group. So that way, when our tetrahedral intermediate collapses and we regenerate our carbonyl, we can readily lose our desired leaving group. So from here, we're just one proton transfer away from our last step. We have our protonated carboxylic acid, and all we have to do is pull off a proton to get our neutral desired carboxylic acid. So this student proposed mechanism looks completely reasonable. So what I'm going to do is I'm going to clear these annotations and then redraw the mechanism just so that way everything's saved on our class whiteboard. But the student proposed mechanism looked great. So as we're working under acidic conditions, the first step is to activate our carbonyl via protonation. Since we're in water, it's probably more reasonable to draw our proton source as H3O+, but that's just a mild technical note. We talked about this in the context of the leveling effect all the way back in chapter 2 of Chem 112. Generally, the most acidic species in solution is going to be the conjugate acid of your solvent. Anyway, so we protonate our carbonyl. Water then attacks the electrophilic carbonyl carbon, and we get this tetrahedral intermediate. From here, we're going to see a series of proton transfers where we pull off a proton to free up a lone pair on our alcohol, and then we protonate our methyl ester in this case. From here, we've now activated our leaving group. So that way, when we regenerate our carbonyl, we can eliminate our leaving group via 1,2 elimination. So we have this activated protonated leaving group. So we can lose our leaving group via 1,2 elimination. And that gives us our carboxylic acid. But we're not quite done yet, because when we kick down the lone pair, we're left with this protonated carboxylic acid. And this protonated carboxylic acid is then deprotonated on our cleanup step to give us our neutral isolable product. Does this mechanism make sense to everyone? Any questions for this reaction? If we don't have any other questions, let's keep going then. So another reaction of esters is aminolysis. This is a method to prepare amides directly from esters. Although this reaction generally is not very efficient and is typically limited to free amides prepared directly via aminolysis with ammonia. So in this case, we're working under mildly basic conditions. And this is a textbook carbonyl substitution reaction. So for the mechanism for this reaction, as we're under mildly basic conditions, the first step is our nucleophile will attack our carbonyl carbon and will form a tetrahedral intermediate. From here, we now have this ammonium salt. Let me draw out some of the hydrogens. And in order to, we can think about it in two ways. We can either kick out our leaving group first or get rid of our leaving group from this tetrahedral intermediate. And I certainly prefer just making this ammonium group a less effective leaving group. So we're going to pull off a proton. We now have the following tetrahedral intermediate. And here we'll kick out our leaving group. It's easier to lose alkoxide as a leaving group versus an amide anion. And so we get our desired amide after loss of our leaving group. Does this mechanism make sense to everyone? Any questions on this reaction mechanism? Okay, if we don't have any other questions, let's try to apply what we've learned, and let's look at a few other classes of reactions of esters. These are going to be reviewed for the most part. So it's important to refresh our memory for common reactions of esters, and one very common reaction that's used often in synthesis is the reduction of esters to convert an ester into an alcohol. Esters can react with lithium aluminum hydride via exhaustive reduction to prepare free alcohols. This mechanism follows a series of 1,2 additions. So hydride attacks the carbonyl carbon. We make a tetrahedral intermediate, and we can lose a leaving group. So in this case, we lose an equivalent of alkoxide. From here, we get an aldehyde, and that aldehyde reacts with another equivalent of hydride via a second 1,2 addition reaction to give, in this case, an addition product. There's no leaving group to kick out in this case, so we isolate our alcohol after a quench with acid. Does this mechanism look familiar to everyone? Does this mechanism for ester reduction look familiar? Okay, let's keep going then. One thing to note is if you want to isolate the aldehyde, you can isolate the aldehyde if you use dibal as your reducing agent at low temperatures. So diacetyl aluminum hydride has a few features going for it. First, it allows controlled delivery of one hydride equivalent. Second, dibal is hindered. And third, dibal can coordinate your carbonyl oxygen. And so when you quench, you actually end up quenching out your desired product from this aluminum salt cake almost. So the actual mechanism for a dibal reduction is almost identical to the generic mechanism for ester reduction. The only caveat being is that dibal allows you to control your reduction to favor only the mono reduction product. So it actually allows us to isolate the aldehyde. Practically, dibal reductions are a little finicky, and as a result, you often see people prepare aldehydes via oxidation rather than direct reduction of esters. Just because you have to be really careful with your equivalents, with your temperature control, and sometimes it requires a little bit of optimization. Is everyone clear on the use of dibal? It allows you to get the mono reduction product. It allows you to isolate an aldehyde via reduction of an ester. And is everyone clear on the mechanism for this reaction? This is a review from earlier chapters. Wonderful, wonderful. So let's keep going now. And let's talk about another common reaction of esters, which is the reaction of esters with Grignard reagents to yield alcohols. As we learned previously, esters react with two equivalents of Grignard reagents to yield a tertiary alcohol. So these are quite useful to prepare symmetrical tertiary alcohols. So for example, if we take something like methyl benzoate and treat it with phenyl magnesium bromide, this will cleanly give the tertiary alcohol triphenyl methanol. So let's talk about the mechanism for this reaction, as this Grignard reaction can simply be thought of as a series of carbonyl substitution reactions. First, our Grignard attacks the electrophilic carbonyl carbon, and that gives us a tetrahedral intermediate. From here, our tetrahedral intermediate will collapse and we'll lose our leaving group to give us an all too familiar ketone. We've in fact used this ketone in one of our earlier laboratories in this course to prepare triphenylmethanol. Now, fortunately or unfortunately, this ketone does not last very long. Under the reaction conditions, a ketone is substantially more reactive than the parent ester, and thus the ketone can be attacked with nucleophiles. So our nucleophile will attack the electrophilic ketone carbonyl carbon, and we will be left with this tertiary alkoxide ion. Now, when we quench with acid, we'll be able to isolate the desired tertiary alcohol. So if you wanted to prepare a symmetrical tertiary alcohol with two identical substituents, Grignard addition into esters is a wonderfully useful method. Does this reaction look familiar to everyone? And does this mechanism for the reaction of Grignard reagents with esters make sense? Any questions on this reaction and the mechanism for this reaction? Any questions that I can address? Okay. So we've talked a lot about the chemistry of esters. Let's now refresh and review the common chemical reactions of amides. So amides are typically prepared from the corresponding acid chloride via reaction with ammonia, monosubstituted or disubstituted amines. You generally can't use tertiary amines because this ammonium species generated is not stable. So you're limited to free primary and secondary amines. Does that discussion make sense to everyone? Does everyone see why a tertiary amine is not usable? Okay, so we can prepare amides from an amine and an acyl chloride. Wonderful. What can we do with these amides? Well, we can hydrolyze them. Heating an amide in aqueous acid or aqueous base produces a carboxylic acid and an amine. Now, one interesting thing about this reaction is if we look at this mechanism, we'll see that just like in the hydrolysis of esters, this reaction utilizes a key proton transfer step to force out our leaving group and to ensure that our leaving group is rendered substantially less nucleophilic. So first, we take our amide and we protonate our amide carbonyl. From here, we can attack our carbonyl carbon with even weak nucleophiles such as water. From here, we're going to engage in a series of proton transfers where our amine is protonated to yield a substantially better ammonium ion leaving group, and we pull off a proton from our alcohol to free up a lone pair. From here, our carbonyl will be reformed and we'll lose our leaving group, such as ammonia. Now, this is where things get really interesting. Once we have our carboxylic acid, ammonia can actually pull off a proton from our carboxylic acid to generate the ammonium ion and our carboxylate ion. This carboxylate ion is immediately protonated under acidic conditions, and that gives us our desired carboxylic acid. However, because we've protonated our lost amine, because we protonate our amine to make the ammonium salt, is this ammonium ion remotely nucleophilic? Is this ammonium ion any bit nucleophilic? Is there any available nucleophilic lone pair? Is there an available nucleophilic lone pair? No. And because we've protonated our leaving group and we've completely protonated our amine under these acidic conditions, we in turn have driven this equilibrium towards the product because the reverse reaction would not occur. Our leaving group has been protonated and rendered functionally non-nucleophilic. Does that idea make sense to everyone? Any questions on this mechanism for amide hydrolysis under acidic conditions? Okay, so let's look at amide hydrolysis under basic conditions. In this case, our nucleophile, which is hydroxide, attacks the amide carbonyl carbon. From here, our tetrahedral intermediate collapses and we kick out the amide anion. From here, the amide anion abstracts a proton and we get our carboxylate ion product. This loss of amide anion is not very favorable, and that's why generally amide hydrolysis under basic conditions typically requires high temperatures and long reaction times. Does this mechanism make sense to everyone? Wonderful. Okay, so let's keep going and let's try to apply what we've learned to the following examples. So here I'd like us to predict the product of the following reaction and draw a mechanism for this reaction. So we have this desired amide reacting with sodium hydroxide and water. So let's take a few minutes to work through this example, and then I'd like students to predict the product from this reaction and share their responses in the chat, verbally, or annotated directly onto the class whiteboard. And if there are any questions that I can address as we work through these examples, don't be shy to ask your questions in the chat or verbally. So, would anyone like to volunteer and share a proposed mechanism for this reaction? Or would anyone like to predict the product from this reaction? So in this case, we're treating an amide with sodium hydroxide. So are we dealing with acidic or basic hydrolysis conditions? What do we think? Acidic or basic conditions? What does the class think? Basic conditions, yeah. So based on that, we have our nucleophilic equivalent of hydroxide. And as the student drew out on the class whiteboard, our nucleophile will attack the electrophilic carbonyl carbon. From here, we make a tetrahedral intermediate, and then we kick out our leaving group, which is our ammonium ion. From here, we have one last step to consider, and for our last step, we're going to deprotonate our carboxylic acid, and that gives us our carboxylate ion and our protonated amine. Would we be able to show that last proton transfer step? Because we're unlikely under the reaction conditions to have a carboxylic acid in the presence of sodium hydroxide, nor in the presence of the amide. So the mechanism looks great so far. No worries. Would anyone like to try to finish the mechanism by showing that last proton transfer step? So our amide anion will go and pull off a proton, and that gives us our carboxylate ion. Yep, exactly right. Yep, so the student proposed mechanism looks completely reasonable. Let's clear these annotations and let's redraw the mechanism for our class note set. So as we're working under basic nucleophilic conditions, the first step in this mechanism is that our nucleophilic source of hydroxide will attack our electrophilic carbonyl carbon. From here, we generate a tetrahedral intermediate. And this tetrahedral intermediate will collapse and we'll lose an equivalent of amide anion. From here, we're going to see our last proton transfer step, where our amide pulls off a proton from our carboxylic acid. And that in turn gives us our carboxylate salt. And our free amine. And of course, when you quench your reaction mixture, your carboxylate salt is protonated, and that gives you your carboxylic acid. Any questions on this mechanism? Any questions on this mechanism for the basic hydrolysis of amides? If not, let's try to apply what we've learned to another example. So in this case, we have an amide. We're treating it with hydrochloric acid and water. I'd like us to predict the product from the following reaction and then draw a mechanism for this reaction. So let's work through this example over the next 3 to 4 minutes. And then I'd like students to share their proposed responses in the chat, verbally, or annotated directly onto the class whiteboard. So let's take a few minutes as we work through this example. So we have a student beginning to annotate the mechanism for this reaction in the first step. They predicted that we'll get the corresponding carboxylic acid at the end of this reaction. And they're showing for the first step, we're going to protonate our amide carbonyl oxygen. From here, even weak nucleophiles, such as water, can attack the carbonyl carbon. That in turn gives a tetrahedral intermediate. And in order to get our desired carboxylic acid product, we're going to have to engage in a series of proton transfers. I think we lost our amine early. Yeah, perfect. So from here, we're going to pull off a proton and we're going to, well, I think before that protons transfer step, we need to activate our leaving group. So I would wait on that deprotonation step. We have to do a series of proton transfers before then, right? Because we have this positively charged water adduct, and we need to activate our amine as a leaving group, right? So first we have to pull off a proton from our alcohol, and then we have to protonate our amine. Oh. What we can do is we can start from.
I cleared an accident. I'm sorry.
No worries, no worries.
I'm sorry.
No worries at all. What I'll do is I'll annotate the steps that we have so far, and then we can pick up from there.
Okay. Thank you.
No worries. So, as we've seen so far, the first step for this hydrolysis reaction under acidic conditions is we are going to protonate our amide carbonyl oxygen. We now have an activated electrophilic carbonyl carbon that can be attacked with even weak nucleophiles such as water. From here, our nucleophile will attack and will generate a tetrahedral intermediate. And now this is where the students in the class can continue on with annotating the mechanism for this reaction. So we have this water adduct, we have this tetrahedral intermediate, and let's show the steps needed to activate our amine as a leaving group and how we prepare this substrate to generate our carboxylic acid product. So let's keep working through this mechanism from here. And if there are any questions that I can address, don't be shy to send them my way. And let's continue on with this mechanism and let's try to annotate the last few steps for this amide hydrolysis mechanism. And for everyone else who are working through this mechanism, don't be shy to share your proposed mechanisms in the chat as well. You can share photos of your written work or comments for this mechanism in the chat, and I'd be happy to annotate your proposed responses. So we have many students commenting the next step where we transfer a proton to our amine to activate it as a leaving group, and we pull off a proton from our cationic alcohol oxygen. Perfect. So after these proton transfer steps, what do we get out from these steps and how do we finish this reaction mechanism? So we have our protonated amide. Well, it's not an NH3 group. It's NH2 with a methyl group, right? Okay, so now that we've set up our leaving group, we're going to pull off a proton and we're going to kick out our leaving group. So I would draw this arrow all the way down here to form our carbonyl and kick out our leaving group. Yep. Perfect. And now what product do we get? This is good. This is good. And if there are any questions as we work through these examples, don't be shy to ask as I'm checking the chat regularly. Okay, so now we have our protonated carboxylic acid. We're almost done with this mechanism. What's the last step? How do we get a neutral isolable product? What's our last step? Not quite protonation. We already have this carboxylic acid that's protonated. How do we get a neutral product? Would anyone in the class like to provide input? How do we get a neutral isolable product from this mechanism? So we have this protonated carboxylic acid, and all we have to do is pull off a proton. We can either have water or our amine pull off a proton. Either would work. Yep, perfect. So this student proposed mechanism looks great, and I appreciate students in the chat chiming in with their input and feedback. So let's show these next few steps. So we have protonation of our amide carbonyl, attack of water, and now we have a series of proton transfers to activate our amine as a leaving group and to free up a lone pair on our alcohol oxygen. From here now, we have everything prepared for our next step, where we lose our leaving group and we regenerate our desired carbonyl. This gives us our protonated carboxylic acid, which is a highly acidic species, which can be deprotonated by water. That in turn gives us our desired carboxylic acid product. Does this mechanism make sense to everyone? Any questions on this mechanism? Okay, let's keep going if there aren't any other questions. And let's talk about one last important reaction for amides and one important way to prepare complex amines. Amides can be converted to amines via reduction with lithium aluminum hydride. To help us understand the mechanism behind this reaction, it's important for us to consider the specific role of aluminum in this reaction. So just like any hydride reduction, our hydride equivalent attacks the amide carbonyl carbon. This gives us a tetrahedral intermediate. And what's important to consider now is that our oxygen lone pair is coordinated to aluminum. And as a result, this activates this oxygen and activates this alcohol as a better leaving group. As a result, we can kick down our amine lone pair and we can lose an equivalent of alkoxide because this alcohol has been activated via coordination with aluminum. Aluminum is a Lewis acid. It can coordinate the lone pairs of this alcohol and in turn activate it as a leaving group. From here, now that we have an aminium ion, the aminium ion can be reduced with a second equivalent of hydride to give us a neutral isolable amine. Does this mechanism make sense to everyone? Does this mechanism for amide reduction make sense? Are there any questions for this mechanism? The key feature of this mechanism, just like the direct reduction of carboxylic acids, is that aluminum coordinates our alcohol, which activates it as a leaving group. You typically don't lose alkoxide ions readily, but when coordinated with aluminum, we now have activated this alcohol as a leaving group. Does that make sense? Any questions? Can I get some confirmation in the chat that everyone's comfortable with this mechanism and everyone understands why this works? Because we use lithium aluminum hydride. Perfect. Okay, so let's keep going and let's talk about a use for this reduction of amides. Because we can prepare amides readily from an acyl chloride and an amine, we can prepare acyclic and cyclic amides and then reduce those amides to complex cyclic and acyclic amines. So to answer the question in the chat, the student has the following question. Does the oxygen atom attack the aluminum hydride in the first step? So you can draw it that way, where the oxygen, technically during this first reduction step, a lone pair is being coordinated by aluminum. And that coordination is part of what activates the amide for reaction with hydride. Does that answer your question? So part of the reason why lithium aluminum hydride is such a strong reducing agent stems from the fact that it coordinates the carbonyl and activates the carbonyl while hydride is being donated in. It may not be correct to draw it as a formal bond. I often like to show just coordination, where the lone pair is being coordinated by your Lewis acid. But both interpretations presented in the book are fine. The main thing to note is that alkoxide ion has been activated as a leaving group via coordination. Does that make sense to everyone? Perfect. So, because we can so readily prepare amides via the reaction of an amine and an acyl chloride, we can reduce our amide down with lithium aluminum hydride and prepare very complicated amines. So this is a useful method to prepare amines. Similar processes of reductive amination are also observed if you take and you try to prepare an imine from an amine and an aldehyde. So this idea of reductive amination is a common method to prepare complicated cyclic and acyclic amines. Does this make sense to everyone? Does everyone see how the reduction of amides allows us to prepare amines that would be quite difficult to make otherwise? Does everyone see the utility of this method and how it allows us to prepare relatively complicated amines quite? Okay, so we've reached a great point for today, but let's close out today's session by applying what we've learned for the reduction of amides by predicting the product of the following reaction and then drawing a mechanism for this reaction. So in this case, we have an amide and we're treating it with lithium aluminum hydride in diethyl ether. I'd like us to predict the product from this reaction and draw a mechanism. So let's work on this problem for about 3 to 4 minutes, and then I'd like students to share their proposed responses in the chat, verbally, and then ideally annotated on the class whiteboard. So if we treat an amide with lithium aluminum hydride, after reduction, we get the corresponding amine. Wonderful. The predicted product proposed looks reasonable. Would anyone like to try and justify this predicted product by drawing a mechanism for this reaction? Would anyone like to try drawing a mechanism for this reaction? So we have a carbonyl functionality and a hydride reducing agent. So the first step is our hydride equivalent will attack the electrophilic carbonyl carbon. The carbonyl oxygen lone pair will coordinate to aluminum. So when we make this tetrahedral intermediate, when we look at this addition product, we'll notice that our alkoxide has been coordinated to aluminum. This activates our alkoxide ion as a leaving group, and it allows us to kick out this otherwise quite terrible leaving group to make an aminium ion. So from here, once we kick out our leaving group and once we kick out the alkoxide ion, that gives us an aminium. Would you be able to draw that double bond more clearly? Yeah, perfect. And that aminium ion can be reduced with a second equivalent of hydride. Yeah. And that in turn gives us our desired isolable amine. Wonderful. These student proposed mechanisms look completely reasonable. Okay, so let's clear these annotations and let's redraw and go over this mechanism one more time for our reference. So we have our amide, and one way that I like to think of it is that our aluminum hydride is coordinating our carbonyl oxygen and then donating an equivalent of hydride. From here, after reduction, we have the following alkoxy or alkoxide ion. And what we can do now is we can kick out this activated alkoxide ion to give an aminium ion. From here, a second equivalent of hydride can attack our aminium ion and give us our desired isolable amine. Does this mechanism make sense to everyone? Any questions on this mechanism?
Professor, so we wouldn't need to draw the two hydrogens bonds sticking out.
You can, but they're implied.
Oh, okay.
Yeah.
Got it.
Mm-hmm.
Thank you.
Any other questions I can address? So we're just about at the end of chapter 21. Any questions on this chapter that I can answer before we archive today's recording and we close out today's session? So if we don't have any other questions, what we'll do is we'll archive